Deep in the darkness of interstellar space, racing toward our solar system at tens of thousands of kilometers per hour, astronomers have detected something that should be impossible, something that has never been observed in any solar system comet ever. We have always believed we understood the basic chemistry of these ancient comets. Nickel and iron bound together since the formation of stellar systems, released together when solar heating awakens a comet's frozen surface. But 3 Atlas follows different rules entirely. Spectroscopic analysis reveals neutral nickel emissions streaming from this cosmic visitor. But the iron signatures that should accompany them are completely absent. However, pure nickel is a familiar phenomenon in terrestrial metallurgy, where it is obtained through refining. This raises a key question. Is this object a product of space manufacturing? While government space agencies speak in careful diplomatic language about safe trajectories and ongoing analysis, the preprint papers tell a different story. Tonight we investigate what scientists aren't telling us about this interstellar visitor. We will examine the spectroscopic evidence, decode the institutional silence, and explore why some researchers whisper about possibilities that stretch far beyond conventional science. Prepare yourselves. We begin. Nickel in the dark. The cosmos has a way of keeping its most intriguing secrets wrapped in the language of spectroscopy. In the early morning hours of August 15, 2025, astronomers peering through the European Southern Observatory's Very Large Telescope in Chile noticed something that shouldn't exist. There, dancing across their computer screens in the form of precise wavelengths of light, were the unmistakable signatures of neutral nickel atoms streaming from Comet 3 Atlas. But here's what made seasoned scientists pause mid-coffee: the iron lines that should have accompanied those nickel signatures were nowhere to be found. In our solar system, nickel and iron are cosmic siblings. They form together, travel together, and when a comet heats up enough to release one, you almost always see both. It's like finding footprints in snow from only one boot. The universe, it seems, doesn't usually separate these metallic twins without a very good reason or a very unusual process. What makes this discovery particularly unsettling is not just the scientific anomaly itself, but the careful way it's being discussed in academic circles. When you read through the preprint papers posted on RXIV, the platform where scientists share their findings before peer review, you'll notice something curious. The language is unusually cautious, even for astronomy. Phrases like mechanism uncertain and unusual physics or chemistry pepper the technical documents like diplomatic warnings. The instrument trail tells its own story. Teams using the ultraviolet and visual Echelle spectrograph and X-shooter instruments at the Very Large Telescope have independently confirmed these nickel emissions. They've also detected the emergence of cyanide, that's CN to chemists, in mid-August spectra. These aren't the kind of observations you misinterpret or accidentally fabricate. Multiple instruments, multiple teams, consistent results. Yet if you scan the mainstream headlines about 3 Atlas, you'll find a curious disconnect. Some outlets hint at alien possibilities with the subtlety of a foghorn, while the actual scientific papers read like diplomatic cables, technically precise but emotionally sterile. The contrast invites a question. What exactly are we looking at when we stare into the spectroscopic soul of this interstellar visitor? There's another puzzle wrapped inside this cosmic riddle. 3 Atlas is shrouded in a coma that's the fuzzy atmosphere around its nucleus, dominated not by water vapor like most comets, but by carbon dioxide. This CO2 shroud acts like a cosmic fog bank, making it nearly impossible to see the actual solid nucleus underneath. It's as if the comet is wearing a chemical cloak, revealing only what it chooses to show us. The James Webb Space Telescope has confirmed what ground-based observations suggested. This object produces carbon dioxide at rates that dwarf its water production by ratios rarely seen in nature. For context, most comets are cosmic snowballs with a bit of dry ice mixed in. 3 Atlas appears to be the opposite, a dry ice ball with just a hint of snow. So we're left with a series of interconnected mysteries. A comet that produces nickel without iron, a composition dominated by carbon dioxide rather than water, a nucleus hidden behind its own emissions like a magician behind smoke and mirrors, and most intriguingly, a scientific community that seems to be choosing its words with unusual care. The guiding question that will follow us through this investigation is deceptively simple. Are we witnessing a natural quirk of cosmic chemistry and formation, or something that challenges our understanding of what's possible in nature. The evidence, as we'll see, doesn't yet point definitively in either direction, but it does whisper of possibilities that stretch the boundaries of conventional comet science. The cosmos, after all, has been whispering in nickel, and sometimes the quietest voices carry the most important messages. Meet Three Atlas. To understand why Three Atlas has astronomers reaching for their most diplomatic language, we first need to understand what makes this visitor so fundamentally different from anything in our cosmic neighborhood. The designation itself tells a story. Three marks it as only the third confirmed interstellar object ever detected passing through our solar system, following the mysterious cigar-shaped Oumuamua in 2017 and the more conventional comet Borisov in 2019. The Atlas portion honors the Asteroid Terrestrial Impact Last Alert System, specifically the station at Rio Hurtado, Chile, where this cosmic wanderer was first spotted on July 1, 2025. Picture the scene: automated telescopes scanning the southern sky, their cameras capturing millions of points of light each night, when suddenly the computer algorithms flagged something moving with a velocity and trajectory that didn't belong to our solar system's gravitational embrace. The official designation reads C2025 N1 Atlas, but the international astronomical community quickly recognized its interstellar nature and promoted it to Three Atlas. This promotion isn't merely bureaucratic. It represents confirmation that this object originated somewhere else entirely, in a stellar system potentially hundreds or thousands of light-years away, and is now making what amounts to a one-time flyby through our celestial neighborhood. The mathematics of its trajectory tell an unambiguous story. Three Atlas follows what astronomers call a hyperbolic orbit, a path so energetic that our sun's gravity can bend but not capture it. Unlike the elliptical orbits of solar system natives, this trajectory is open-ended, a cosmic highway that leads from interstellar space around our sun and back out into the galactic void. No return trips, no second chances for detailed study. From Earth's perspective, this interstellar visitor poses absolutely no threat. Its closest approach to our planet will be approximately 1.8 astronomical units, roughly 270 million kilometers away. To put this in perspective, that's farther than the distance between Earth and the Sun. Mars, during its closest approaches to Earth, gets within about 55 million kilometers. Three Atlas will maintain a respectful cosmic distance, like a polite visitor who admires your garden from the sidewalk, rather than trampling through your flower beds. The timing of its solar encounter adds another layer to this cosmic story. Perihelion. The point of closest approach to the Sun is scheduled for around October 30th, 2025 at approximately 1.4 astronomical units from our star. That places it just inside Mars's orbital distance, close enough to receive significant solar heating, but far enough away to avoid the extreme conditions that might completely vaporize a small nucleus. Speed-wise, Three Atlas is racing through our solar system at tens of kilometers per second relative to the Sun. Those racing through headlines you might have seen are technically accurate, but they can be misleading. This velocity is entirely normal for interstellar objects. What makes it remarkable isn't the speed itself, but the fact that this speed originated from motion through the galaxy rather than from our Sun's gravitational acceleration. The timeline of visibility presents both opportunities and challenges for Earth-based observers. After perihelion in late October, Three Atlas will appear to move closer to the Sun as seen from Earth, making observations increasingly difficult through November as it approaches what astronomers call solar conjunction, the point where it disappears behind the Sun's glare. However, this celestial game of hide-and-seek ends in early December 2025 when the comet emerges on the other side of the Sun for what may be our final extended observation period. One of the most frustrating aspects of studying Three Atlas is how little we can directly observe of its nucleus. The Hubble Space Telescope, despite its extraordinary capabilities, can only establish an upper limit of approximately 5.6 kilometers for the nucleus diameter. This isn't a failure of our most advanced space-based observatory. It's a testament to how effectively the comet's own emissions obscure its solid core. Imagine trying to study a campfire by looking at the smoke rather than the flames. That's essentially what we're doing with Three Atlas. The nucleus itself remains stubbornly invisible, hidden somewhere within that cocoon like a cosmic Russian doll whose innermost layer refuses to be revealed. This observational challenge becomes even more significant when we compare Three Atlas to its interstellar predecessors. Oumuamua appeared to be largely inert, producing no detectable coma despite its bizarre elongated shape and mysterious non-gravitational acceleration. Borisov, on the other hand, behaved exactly like a solar system comet, complete with a beautiful tail and a composition matching what we'd expect from our own Kuiper Belt objects. 3 Atlas occupies a middle ground that's somehow more puzzling than either extreme. It's clearly active, producing the gas and dust emissions we associate with comets. But the chemistry of those emissions tells a story unlike any comet we've studied before, a story written in nickel lines without iron, in carbon dioxide ratios that dwarf water production, and in cyanide signatures that emerged precisely when theoretical models suggested they should. As we'll discover, this cosmic visitor's reluctance to reveal its secrets may be the most telling characteristic of all. The carbon dioxide shroud. Most comets are cosmic snowballs with a secret. Beneath their dirty ice exteriors lies a chemistry dominated by water, the molecule that makes Earth's oceans possible and life as we know it thinkable. 3 Atlas, however, seems to have read a different script entirely. The James Webb Space Telescope's spectroscopic analysis reveals a coma dominated not by water vapor but by carbon dioxide, and in ratios that stretch the boundaries of what astronomers consider typical for these ancient time capsules. The numbers, while still being refined through peer review, suggest a carbon dioxide to water ratio of approximately 8:1. To understand how extraordinary this is, consider that most solar system comets produce water and carbon dioxide in roughly opposite proportions. It's like discovering a snowman made primarily of dry ice with just a dusting of regular snow. Technically possible, but so unusual it demands an explanation. This carbon dioxide dominance creates what we might call a cosmic fog bank. Unlike water vapor, which is relatively transparent at many wavelengths of light, carbon dioxide forms a dense, optically thick shroud around the nucleus. The result is that even our most sophisticated instruments struggle to peer through this chemical veil to glimpse the solid core underneath. It's as if 3 Atlas is wearing a cloak woven from its own emissions, revealing only what it chooses to show us. The SphereX mission's preliminary observations add another piece to this puzzle. Their imaging shows an extended carbon dioxide coma with no obvious jets or streamers, those characteristic features that usually point back toward active regions on a comet's nucleus. Instead, 3 Atlas appears to be outgassing uniformly from its entire surface, or at least in a pattern so symmetric that individual jets blend into a smooth, featureless glow. The Hubble Space Telescope's images reinforce this sense of concealment. What we see is essentially a dusty cocoon with background stars streaked into trails due to the telescope's tracking of the comet's motion. The nucleus itself remains stubbornly invisible, hidden somewhere within that cocoon like a cosmic Russian doll whose innermost layer refuses to be revealed. Several working hypotheses attempt to explain this carbon dioxide dominance, but each raises as many questions as it answers. One possibility involves the comet's formation environment. If 3 Atlas originated in a stellar system with a different temperature profile than our own, perhaps around a star cooler than our Sun, it might have formed near what astronomers call a carbon dioxide ice line. In such an environment, carbon dioxide would freeze out before water, potentially creating objects with compositions dramatically different from our solar system's comets. Another hypothesis focuses on thermal evolution and surface physics. Some comets develop insulating crusts over their lifetimes, layers of dust and processed organic materials that act like cosmic thermos bottles. Such a crust might suppress water vapor outgassing while allowing the more volatile carbon dioxide to escape more easily. As 3 Atlas approaches the Sun, this selective outgassing could create the skewed chemistry we observe. The production rates themselves tell a story of a small but active nucleus, while the absolute numbers vary depending on the instrument and analysis method, a reminder that we're watching science in real time as calibrations are refined. The order of magnitude suggests a modestly sized object producing gas at rates consistent with its apparent size. There's nothing here that screams impossible, but everything whispers unusual. Media coverage has latched onto the cloak metaphor with enthusiasm, sometimes implying a deliberate concealment rather than a natural consequence of chemistry and physics. This linguistic choice reveals something about how we process cosmic mysteries. When nature behaves in unexpected ways, we tend to anthropomorphize the phenomenon, attributing intention, where there may be only the inevitable result of unfamiliar physics playing out in an alien environment. The carbon dioxide shroud also complicates every other measurement we want to make. dust production rates, nucleus rotation periods, surface temperature, mapping the search for jets or active regions. All of these observations become more challenging when filtered through a dense, chemically active atmosphere. It's like trying to study a lighthouse bulb from inside a thick fog. You can see that something bright is happening, but the details remain maddeningly obscured. What makes this even more intriguing is the timing of our observations. Different instruments observing at different epochs can produce apparently contradictory results that later reconcile as we understand the temporal evolution of the coma. A spectrum taken in July might show 1 carbon dioxide to water ratio, while an August observation reveals a different value, not because the measurements are wrong, but because comets are dynamic systems that change as they approach and recede from the sun. The carbon dioxide mystery deepens when we consider the implications for the nucleus composition. If the coma is dominated by carbon dioxide, what does that tell us about the solid ice mixture from which these gases are sublimating? Are we looking at a fundamentally different type of planetary building block, one that formed under conditions so unlike our solar system's early environment that it challenges our models of how planetary systems assemble? Or perhaps, as we'll explore further, the carbon dioxide shroud is telling us something else entirely, something about processes that don't typically occur in nature, or about a visitor whose origins may be more exotic than even interstellar space usually provides. The fog bank surrounding Three Atlas isn't just obscuring our view of its nucleus. It may be obscuring our understanding of what's possible in the cosmos itself. The official line. When government space agencies speak about Three Atlas, their language carries the careful precision of diplomatic communiques. NASA's official statements read like a checklist designed to inform, without alarming interstellar comets' safe trajectory. Perihelion, approximately October 30th, 2025. At roughly 1.4 astronomical units from the Sun, closest approach approximately 1.8 astronomical units. No threat to our planet. The facts are presented with the emotional temperature of a weather report, technically accurate, reassuringly mundane. This measured tone isn't accidental. Space agencies learned hard lessons from previous encounters with unusual celestial visitors. The public reaction to Oumuamua's bizarre characteristics spawned everything from serious scientific debates about hydrogen icebergs to wild speculation about alien spacecraft. With Three Atlas showing its own collection of anomalous properties, NASA and its international partners have apparently decided that conservative communication is the better part of valor. The European Space Agency echoes NASA's cautious approach, emphasizing the same safe distances and lack of threat to Earth, while noting the object's speed and late October perihelion timing. Their press releases read like exercises in measured reassurance, providing enough information to satisfy public curiosity while avoiding anything that might fuel speculative fires. The Minor Planet Center, which serves as the official clearinghouse for observations of asteroids and comets, has been similarly restrained. Their minor planet electronic circulars dutifully record astrometric observations, the precise positions needed to calculate and refine the object's trajectory, but avoid interpretive commentary. They're the cosmic equivalent of court stenographers recording what happened without editorial comment. The Hubble Space Telescope program's public communications follow a similar pattern. Their Astronomy Picture of the Day feature shows the comet as a fuzzy blob against star-streaked backgrounds with captions that emphasize the hyperbolic orbit and size constraints, while carefully avoiding speculation about the object's unusual properties. Even when presenting visually spectacular images, the accompanying text maintains a tone of scientific neutrality. This conservative approach extends to the James Webb Space Telescope team's blog posts and press releases. Despite conducting some of the most detailed spectroscopic observations of Three Atlas, their public communications stick to safe harbor phrases: analysis underway, preliminary results, further observations planned. They link to preprint papers rather than making bold claims, letting the technical literature speak for itself while avoiding institutional endorsement of any particular interpretation. Behind this cautious public face lies a more complex reality. The same agencies funding detailed observations with the world's most advanced telescopes are clearly taking Three Atlas seriously enough to dedicate precious observing time from instruments that are oversubscribed by factors of 10 or more. The James Webb Space Telescope doesn't point at random objects. Every minute of its operation represents thousands of dollars and months of competitive proposal processes. The visibility timeline adds urgency to these observations. 3 Atlas will likely become too close to the Sun for safe observation from Earth sometime in late September, remaining hidden behind solar glare until early December 2025. This creates a narrow window for detailed study before perihelion and another brief opportunity afterward when the comet emerges from conjunction. The agencies know this is essentially a one-shot deal. Miss the opportunities this year and 3 Atlas disappears into interstellar space forever. What's particularly interesting is what the official statements don't say. There's no mention of the nickel emission lines detected by European Southern Observatory teams. No discussion of the unusual carbon dioxide to water ratios. No acknowledgement of the cyanide detections or their timing. This isn't necessarily secrecy. It's standard practice to let peer review processes run their course before making official pronouncements about potentially significant discoveries. The glossary-heavy nature of official communications also serves a strategic purpose. By carefully defining terms like perihelion, astronomical unit, coma, and production rate, agencies can provide education while maintaining focus on established science rather than speculative interpretations. It's a way of keeping the conversation grounded in measurable phenomena rather than letting it drift into theoretical territory. Multi-observatory coordination tells its own story about institutional priorities. The James Webb Space Telescope, Hubble Space Telescope, and SphereX missions have all been directed to observe 3 Atlas, suggesting high-level interest despite the measured public tone. When space agencies coordinate observations across multiple billion-dollar facilities, they're making a statement about scientific importance, even if they won't explicitly say so in press releases. The peer review timeline creates additional tension between public curiosity and institutional caution. Preprints appear on Arxiv within days or weeks of observations, but formal publication in peer-reviewed journals can take 6 months or more. During this gap, the most interesting findings exist in a scientific limbo, significant enough for researchers to share with colleagues but not yet validated enough for agencies to stake their reputations on. Perhaps most tellingly, the absence of bold claims in official communications shouldn't be interpreted as evidence against extraordinary possibilities. Space agencies learned from Oumuamua that unusual objects can spawn unusual theories, some of which later prove correct, and others which prove embarrassingly wrong. In this environment, saying "we don't know yet" becomes both intellectually honest and institutionally prudent. The official line, in other words, may be less about what space agencies know and more about what they're willing to say before the scientific process runs its complete course. The lab notes and preprints. While government agencies practice diplomatic restraint, the scientific community operates in a different realm entirely, one where curiosity moves faster than institutional caution, and discoveries are shared through preprint servers before bureaucratic approval processes can slow them down. In the case of 3 Atlas, this parallel universe of laboratory notes and preliminary findings tells a far more intriguing story than official press releases suggest. The European Southern Observatory teams working with the Very Large Telescope's UVES and X-Shooter instruments have been remarkably forthcoming in their RxIve submissions. Their mid-August observations documenting neutral nickel emission lines without corresponding iron signatures represent the kind of finding that makes experienced spectroscopists double-check their calibrations. When multiple independent instruments confirm the same anomalous result, it moves from interesting if true to demanding explanation. The timing of these observations matters enormously. Early July spectra captured what amounts to a baseline 3 Atlas at a greater solar distance with relatively quiet outgassing and conventional comet behavior. The mid-August observations as the comet moved closer to the Sun and its surface temperatures began rising showed the emergence of both the nickel lines and detectable cyanide emission. This temporal correlation suggests we're watching chemical processes unfold in real time driven by increasing solar heating. An independent confirmation of the cyanide onset appeared in a September 3rd letter to the astronomy community, reporting the mid-August emergence consistent with Very Large Telescope observations and additional confirmations from Lowell Observatory. When multiple research groups using different telescopes report the same temporal evolution of spectral features, it becomes difficult to dismiss them as instrumental artifacts or calibration errors. The SphereX preliminary note adds another dimension to this emerging picture. Their observations of an extended carbon dioxide coma with no obvious jets or streamers complement rather than contradict the spectroscopic findings. What we're seeing is a remarkably uniform outgassing pattern that produces unusual chemistry: carbon dioxide dominance, nickel without iron, and evolving cyanide production, all from what appears to be a small, featureless nucleus. These preprint submissions follow a well-established rhythm in astronomy. Observations are made, data are processed and analyzed, preliminary findings are shared with the community through arXiv, and then the formal peer review process begins. This system allows for the rapid dissemination of potentially important discoveries while maintaining the quality control that comes from expert evaluation. It also means that the most interesting findings often appear in technical papers months before they make their way into official agency statements. The production rate calculations illustrate both the power and the pitfalls of this preprint system. Different research groups using different instruments and slightly different analysis techniques can produce measurements that appear to disagree. Not because anyone is wrong, but because the absolute calibration of production rates depends on assumptions about nucleus size, outgassing patterns, and atmospheric models. These apparent discrepancies usually resolve themselves as the analysis techniques converge and more data become available. What's particularly fascinating is how blog posts and informal commentary have begun interpreting these preprint results. Some analysis pieces suggest that the combination of unusual chemistry and a hidden nucleus might indicate industrial processes or technological artifacts. These interpretations go well beyond what the data currently support, but they illustrate how quickly scientific observations can be extrapolated into speculative territory. The cadence of observations matters enormously for understanding comets, which are fundamentally dynamic systems. A spectrum taken in July shows one snapshot of chemistry and activity. An August spectrum reveals changes driven by increasing solar heating. September observations capture further evolution as the comet approaches perihelion. Only by combining multiple epochs can we understand the full story of how 3 Atlas responds to its changing thermal environment. Different instruments contribute different pieces of this puzzle. Ultraviolet and visible light spectroscopy excel at detecting metallic emissions like nickel and iron. Infrared observations from space-based telescopes can penetrate dust better and detect molecular emissions that are invisible to ground-based observations. Radio telescopes might detect molecules that don't emit invisible light. Each wavelength range tells part of the story, but the complete picture emerges only when all these observations are combined. The peer review process that follows preprint submissions serves as both quality control and a reality check. Expert reviewers examine methodology, question assumptions, and suggest alternative interpretations, occasionally identifying systematic errors that invalidate entire analyses. This process can take months or even years, during which preliminary findings remain in a scientific limbo, interesting enough to discuss among colleagues but not validated enough for institutional endorsement. In the fast-moving world of comet observations, where objects appear and disappear on timescales of months, this creates an inevitable tension between scientific rigor and public curiosity. What emerges from this laboratory phase is a picture of 3 Atlas that's simultaneously more detailed and more puzzling than official summaries suggest. The nickel detections appear robust. The carbon dioxide dominance seems real. The temporal evolution of chemical signatures follows predictable patterns driven by solar heating. But the underlying mechanisms that produce these observations, particularly the decoupling of nickel from iron, remain mysterious. The lab notes, in other words, are humming with activity and generating more questions than answers. And in science, that's often exactly where the most interesting discoveries begin. Interpreting nickel natural versus unnatural. The detection of neutral nickel emission lines in 3 Atlas's spectrum represents something like finding a single type of fingerprint at a crime scene, technically clear evidence of what happened, but puzzling in its isolation. In solar system comets, nickel and iron emissions appear together with the reliability of a chemical law. When comets heat up enough to sublimate metallic grains embedded in their ice, both metals typically appear in spectroscopic observations because they form together in stellar nucleosynthesis and remain together through the planetary formation process. 3 Atlas breaks this rule, and the question becomes whether we're witnessing exotic but natural chemistry or something that challenges our understanding of what's possible without technological intervention. The natural pathways for nickel-iron decoupling, while speculative, aren't beyond the realm of known chemistry and physics. One possibility involves selective volatility, the idea that under specific temperature and pressure conditions, nickel-bearing compounds might sublimate, while iron-bearing compounds remain locked in solid form. This could occur if the comet's composition includes organic molecules that preferentially bind with iron, keeping it from escaping into the gas phase while allowing nickel to outgas freely. Another natural mechanism might involve surface chemistry, driven by space weathering over millions of years in interstellar space. Cosmic ray bombardment and exposure to the interstellar medium could chemically alter surface materials in ways that change how metals are bound and released. If 3 Atlas spent significantly longer in interstellar space than typical Oort cloud comets spend between stellar encounters, such weathering could create a surface chemistry unlike anything we see in solar system objects. The compositional heterogeneity hypothesis suggests that 3 Atlas might have formed in a stellar environment with a different metallicity than our solar system. Some stars form with different ratios of heavy elements depending on their location in the galaxy and the composition of the molecular cloud that birthed them. A comet formed around a metal-poor star might naturally contain nickel and iron in unusual proportions or chemical forms. Perhaps the most intriguing natural possibility involves carbonyl chemistry. In environments rich in carbon monoxide, which 3 Atlas appears to be given its carbon dioxide dominance and cyanide production, transient metal carbonyls might form under specific conditions. Nickel carbonyl is a known compound that's more volatile than most iron carbonyls, potentially creating conditions where nickel escapes into the coma while iron remains bound to the nucleus. This mechanism remains entirely speculative and would require laboratory confirmation, but it represents the kind of exotic chemistry that might occur in unusual thermal and chemical environments. The unnatural pathway, stated clearly as a thought experiment rather than a conclusion supported by evidence, would require some form of technological processing that selectively concentrates or releases nickel. Industrial processes on Earth do create nickel-rich alloys and compounds with minimal iron content. Stainless steel production, electroplating, and specialized metallurgy all involve techniques that could, in principle, create materials with the chemical signatures we're observing. The question isn't whether such processing is possible, it's whether there's any evidence for it beyond the nickel detections themselves. A responsible evaluation of the engineered hypothesis would require multiple independent lines of evidence. Isotopic ratios that differ from solar system norms might suggest nucleosynthesis processes that don't occur naturally. Structured radar echoes could indicate a geometric regularity inconsistent with natural objects. Non-gravitational accelerations with patterns that suggest propulsion rather than outgassing would be compelling. Radio emissions synchronized with the object's geometry might indicate an artificial transmission. None of these additional technosignatures have been reported for 3 Atlas. The observational context matters enormously for evaluating these possibilities. Solar system comets do occasionally show unusual metal line ratios, though typically not as extreme as the nickel without iron pattern observed in 3 Atlas. The decoupling isn't physically impossible, it's statistically unusual. This distinction matters because unprecedented doesn't automatically imply artificial, especially when dealing with objects from stellar environments that might differ significantly from our local chemical neighborhood. What would strengthen the natural case is reproducibility across multiple instruments and observing epochs combined with theoretical models that can account for the observations without invoking exotic processes. If the nickel emissions continue to appear consistently as 3 Atlas approaches perihelion, and if the thermal evolution matches predictions from models of selective outgassing or unusual surface chemistry, the case for natural but exotic chemistry becomes more compelling. Conversely, what would strengthen consideration of technological origins would be the appearance of additional anomalies that collectively point toward artificial processes. A single unusual chemical signature might be explicable through natural means, but multiple independent anomalies that all suggest technological origins would be much harder to dismiss. The key word is independent. The anomalies would need to be explainable by technology but not by any natural process. The commentary suggesting industrial nickel signatures represents interesting speculation rather than scientific consensus. Such ideas deserve consideration as hypotheses to be tested rather than conclusions to be accepted, and they must be held to the same evidentiary standards as any other scientific claim. The burden of proof for extraordinary claims remains extraordinarily high regardless of how compelling the speculation might be. Current observations provide one piece of a much larger puzzle. As 3 Atlas continues its approach to perihelion, Additional data will either support or refute various hypotheses about its nickel emissions. Peer review processes will evaluate the robustness of the original detections. Cross-calibration between different instruments will test whether the observations are reproducible. Theoretical work will explore whether known chemistry and physics can account for what we're seeing. For now, the nickel whispers of possibilities without shouting conclusions. And in the careful language of science, whispers often carry more weight than proclamations. Why scientists hold back? The path from raw astronomical data to a confident scientific conclusion follows a labyrinthine route that the public rarely sees, involving calibrations within calibrations, a systematic error analysis that can take longer than the observations themselves, and institutional review processes that are designed to prevent the kind of spectacular mistakes that can end the careers and undermine a public trust in a science. When it comes to a Three Atlas, this normally invisible machinery of a science becomes particularly relevant because the observations are both technically challenging and potentially significant enough to reshape our understanding of the interstellar objects. Consider the basic pipeline that transforms the photons that were collected by a telescope into the spectroscopic signatures that drive the scientific conclusions. First, the raw data must be calibrated against the known standard stars to establish the accurate wavelength and the flux scales. Then the sky background, which is including everything from the atmospheric emission lines to a scattered light from the nearby sources, must be subtracted with a mathematical precision. Only then can the astronomers begin the process of identifying the specific spectral lines and measuring their intensities that are relative to the continuum background. Each of these steps introduces the potential systematic errors that can masquerade as the genuine signals. A small error in a wavelength calibration might shift an apparent nickel line to a different element entirely. An incomplete sky subtraction could create the false emission features or suppress the real ones. A continuum placement, which is determining what counts as the baseline against which the emission lines are measured, can dramatically affect the apparent strength of the weak spectral features. When the claims of an unusual chemistry rest on precisely these kinds of the measurements, an extraordinary care becomes essential. The telescope time allocation system adds another layer of an institutional caution. An observing time on the facilities like the Very Large Telescope or the James Webb Space Telescope is awarded through the competitive processes that can take the months of a preparation and a review. When the astronomers receive this precious resource, they typically have the proprietary periods during which they can analyze their data without an external pressure. This system encourages a thorough analysis rather than the rushed conclusions, but it can also create the frustrating delays between the observations and a public announcement of the results. The signal-to-noise ratio consideration becomes particularly critical when dealing with the weak spectral features that are near the detection threshold. The same dataset can appear to show the strong emission lines or no emission at all, depending on how the analysis is conducted. The different continuum fitting techniques, the different methods for combining the multiple exposures, and even the different software packages for a data reduction can yield the seemingly contradictory results from the identical observations. The multiple independent teams must verify the unusual claims before the scientific community accepts them as robust. A reputation and a replication concern loom especially large in the aftermath of the Oumuamua debates, where the initial observations of an unusual acceleration spawned the theories that were ranging from the hydrogen icebergs to the alien spacecraft. Some of those theories were eventually supported by an additional analysis, while the others were quietly abandoned as better data became available. The experience taught the astronomical community that the interstellar objects can generate an intense public interest and a scientific controversy in an equal measure, which is making a careful evaluation of the claims more important than a rapid announcement. The peer review process, while it is often frustratingly slow, serves as a quality control that can catch the errors that are invisible to the original research teams. The expert reviewers examine a methodology, a question, an assumption, and suggest an alternative interpretation, and occasionally identify the systematic errors that invalidate the entire analyses. This process can take the months or even the years during which the preliminary findings remain in a scientific limbo, and interesting enough to discuss among the colleagues, but not yet validated enough for an institutional endorsement. An observing geometry adds a temporal complexity to these systematic concerns. The apparent strength of the spectral lines depends not just on the physical processes that are producing them, but on the viewing angle, a phase angle, and a distance between the Earth and the comet. An emission line that appears to be strong in a July observation might seem to be weak in an August data, not because the underlying physics has changed, but because we are viewing the same process from a different perspective or at a different distance. An inter-instrument cross-check provides an essential validation, but it requires a careful attention to the systematic differences between the facilities. The Very Large Telescope's UVES instrument operates differently from the X-shooter spectrograph, which in a turn has the different characteristics from the space-based instruments like those on the James Webb or the Hubble. Confirming a detection across the multiple instruments requires an understanding how each facility's unique systematic errors might affect the apparent strength or the wavelength of the spectral features. The James Webb Space Telescope team's blog posts exemplify this institutional caution. Despite conducting some of the most detailed observations of a 3 Atlas, their public communications stick to the phrases like an analysis underway and the preliminary results. They link to the preprint papers rather than making the institutional claims letting a technical literature to speak for itself, while avoiding the situations where the space agency might need to retract or to revise the public statements if a peer review reveals the problems with the initial analyses. A visual representation of the same data can tell the dramatically different stories depending on the processing choices. The same spectrum can be made to emphasize the weak emission lines by expanding the vertical scale, or to de-emphasize them by showing the full dynamic range of the data. The different continuum fits can make the emission features to appear or to disappear entirely. When dealing with the potentially significant discoveries, the researchers must ensure that their data presentation choices reflect the genuine strength of the evidence rather than their hopes about what the data might show. The bottom line is that a scientific caution does not indicate a cover-up or a conspiracy. It reflects a hard-won wisdom about how easy it is to fool ourselves when dealing with the complex data that are near the limits of an instrumental sensitivity. In an astronomy where the objects appear and disappear on the timescales that do not accommodate a lengthy analysis, this creates an inevitable tension between a scientific rigor and a public curiosity. But it also ensures that when the astronomers do make the strong claims about the unusual objects like a 3 Atlas, those claims rest on the foundations that are solid enough to support the weight of an extraordinary implication. Media versus the methods. The chasm between how the scientific discoveries unfold in the laboratory notebooks and how they appear in a public media represents more than just a translation problem. It reflects the fundamentally different approaches to an uncertainty in evidence and the pace at which a knowledge should be constructed. When a 3 Atlas began showing the unusual spectroscopic signatures, this disconnect became particularly stark with the sensational headlines that were competing against a methodical data analysis in what amounts to the parallel universes of an information. Consider the spectrum of a media coverage that emerged as the preprint papers began to appear on the RxEve. At one of the extremes, the tabloid-style outlets seized on the mystery aspects with the headlines that practically vibrated with an excitement. An alien craft that was disguised as a comet baffles the scientists. Read one of the particularly breathless examples of transforming a careful spectroscopic observation into a science fiction scenario with all of the subtlety of a carnival barker. These outlets treated every unanswered question as an evidence of a conspiracy, and every cautious scientific statement as a proof that the authorities were hiding the dramatic revelations. A more responsible science journalism struck a different balance in emphasizing the carbon dioxide dominance and an unusual chemistry, while acknowledging the limitations of current data. The publications like the Live Science and the Smithsonian Magazine managed to convey the genuine scientific intrigue without veering into a speculation that was unsupported by evidence. Their articles explained why a carbon dioxide-rich coma matters, what a nickel emission line tells us about a comet's composition, and why the scientists speak cautiously about the preliminary findings. The contrast becomes particularly sharp when comparing these measured reports to the official space agency communications. The NASA and the European Space Agency's press releases stick religiously to the established facts: an orbital parameter, a safety assurance, an observing schedule, and an instrument capability. Their language carries all of the excitement of a technical manual, which serves the important function of providing an accurate information, while avoiding the kind of speculation that can later prove to be embarrassing if it was contradicted by additional data. This institutional conservatism creates the information gaps that a speculative coverage rushes to fill. When the official sources limit themselves to an analysis ongoing and a further observations planned, the more adventurous outlets feel free to explore the possibilities that range from an exotic chemistry to a technological artifact. The problem is not necessarily that such a speculation occurs. A science often advances through a bold hypothesis, but that a speculation and an established fact can become confused in the public mind when they are presented with the similar levels of an apparent authority. The alien craft hypothesis provides a useful case study in how a scientific caution gets interpreted through the different media filters. The actual evidence consists of an unusual but not an impossible chemistry, an obscured nucleus, and the outgassing patterns that differ from the typical solar system comets. A responsible reporting presents these as the interesting anomalies that are worthy of a further study. A sensational coverage transforms them into the smoking guns for an extraterrestrial technology, as if the absence of the conventional explanations automatically implies the artificial origins. A social media amplifies these distortions through the mechanisms that prioritize an engagement over an accuracy. The dramatic claims about the alien visitors generate more clicks, the shares, and the comments than the careful discussions of a spectroscopic calibration. The algorithms that determine what a content gets promoted have no built-in preference for a scientific rigor, creating an information ecosystem where the most exciting interpretations often drown out the more measured analysis. Even the reputable outlets face the challenges when reporting on an evolving science. The carbon dioxide to a water ratio that was reported as approximately 8:1 in an early coverage might be revised to a 6:1 or a 12:1 as the calibration methods improve and an additional data become available. These revisions do not indicate that the original reporting was wrong. They reflect the normal process of a scientific refinement, but they can erode a public confidence in the scientific claims if the iterative nature of a research is not clearly explained. The confirmation bias problem works both of the ways in this media ecosystem. The outlets that lean towards a sensational coverage tend to emphasize any new data that supports the exotic interpretations, while downplaying the findings that suggest the conventional explanations. Conversely, the more conservative outlets might underemphasize the genuinely anomalous findings to avoid appearing incredulous. Both of the approaches can distort a public understanding by filtering a complex reality through the predetermined editorial positions. The peer review timeline creates the additional complications for a media coverage. The preprint papers appear on the RXIV within the days or the weeks of the observations, providing an immediate access to the technical findings, but without the quality control that comes from an expert evaluation. The journalists that are working under a deadline pressure might report the preliminary findings as if they carry the same weight as the peer-reviewed conclusions, creating the situations where the later revisions or the retractions can seem like a scientific flip-flopping rather than the normal evolution of an understanding. A language itself becomes a battlefield in this process. When the scientists write about an unusual chemistry or the mechanisms that are not yet fully understood, they are expressing an appropriate caution about the phenomena that do not fit the established models. When the media outlets transform this language into a baffling the scientists or a defying an explanation, the emphasis shifts from an ongoing research to a complete mystification and implying that the scientific process has reached a dead end rather than an interesting beginning. The trust tier that emerges from this analysis suggests a hierarchy of reliability that an informed consumer can use to navigate the conflicting reports. The primary sources, the observatory press, releases the peer-reviewed papers, and the official space agency statements occupy the top tier A, representing an information that has passed through an institutional quality control. The secondary sources, like the established science journalism outlets, provide a valuable interpretation and a context, but with the varying degrees of a speculative content. The commentary and the opinion pieces, regardless of their quality, represent the personal interpretations that should be clearly distinguished from the established findings. Perhaps most importantly, a media literacy, in the context of an astronomical discovery, requires an understanding that "we don't know yet" often represents the most honest statement that the scientists can make about an ongoing research. This phrase does not indicate a failure or a cover-up. It reflects the careful process by which a durable knowledge gets constructed from an incomplete information. In a media environment that rewards a certainty and a dramatic revelation, such an intellectual humility can seem unsatisfying, but it may be the most valuable information of all. The challenge for the consumers of a science media lies in a learning to enjoy a mystery without demanding a premature resolution, to appreciate the complexity of a real research without losing an interest when the answers do not arrive on the news cycle timelines. A Three Atlas will continue revealing its secrets on a schedule that is determined by an orbital mechanics and an observational opportunity, not by the editorial calendars or the social media trending topics. The carbon dioxide puzzle box. The carbon dioxide shroud that is surrounding a Three Atlas operates like a cosmic puzzle box, where each attempt to understand one aspect of the chemistry reveals the additional layers of a complexity that are beneath. This is not simply a matter of an unusual composition. It is a systematic pattern of the observations that challenges our understanding of how the comets form, evolve, and interact with their stellar environments. The more that we learn about this chemical veil, the more questions that it raises about what lies beneath. The fundamental puzzle begins with the production rates that seem almost inverted compared to the typical comets. Most of the solar system comets produce a water vapor as their dominant outgassing component, with a carbon dioxide that is playing a supporting role. A Three Atlas appears to operate by the different rules entirely, generating a carbon dioxide at the rates that dwarf a water production by the factors that strain the boundaries of what we consider a normal for these ancient objects. It is like discovering a reverse snowman that is made primarily of a dry ice with just a dusting of a regular snow. This compositional inversion affects every aspect of how we study the comet. A carbon dioxide gas is optically thick at many of the wavelengths, which means that it absorbs and scatters a light in the ways that make it difficult for our instruments to peer through to the nucleus that is underneath. Unlike the relatively transparent water vapor comas of the typical comets, a Three Atlas wears its carbon dioxide atmosphere like a chemical cloak, revealing only what it chooses to show us, and concealing everything else behind a dense, chemically active fog. The Spherex observations add another dimension to this puzzle by revealing what they do not show: the obvious jets or the streamers that would indicate the active regions on the nuclear surface. Most of the comets develop the asymmetric outgassing patterns, as a solar heating concentrates on the areas with the different compositions, the orientations, or the thermal properties. A Three Atlas, however, appears to outgas uniformly from its entire surface, creating the featureless symmetric coma that makes it so difficult to study the underlying solid object. This uniformity might indicate a nucleus that is remarkably homogeneous in a composition with a carbon dioxide that is distributed evenly throughout the object, rather than concentrated in the specific regions. Alternatively, it might suggest a surface layer or a crust that regulates an outgassing in the ways that smooth out the underlying compositional variations. Either interpretation points toward the formation or the evolutionary processes that differ significantly from the mechanisms that created the solar system comets. The temporal evolution of the carbon dioxide production provides the crucial clues about the underlying physics. As a Three Atlas moves closer to the Sun, an increasing solar heating should drive the changes in the outgassing rates and the chemical signatures. The emergence of the cyanide emissions in mid-August, coinciding with the nickel detections, suggests that we are watching a complex chemical system that is responding to the changing thermal conditions in real time. The geometry of the observations matters enormously for interpreting these changes. The phase angles, the angle between the Sun, a comet, and the Earth, affect how we see both a reflected sunlight and a thermal emission from the nucleus and the coma. A jet, or an active region that is invisible from one viewing angle, might become obvious from another. This means that the reports of no obvious jets must be understood as an epoch-specific and a viewing geometry-dependent rather than the definitive characteristics of the object. The Hubble's imaging constraints illustrate the observational challenges that were created by the carbon dioxide shroud. Even our most advanced space-based telescope can establish only the upper limits on a nucleus's size rather than the direct measurements, because the solid core remains hidden behind its own emissions. It is like trying to study a light bulb from inside a thick fog. You can see that something bright is happening, but the details remain frustratingly obscured. The James Webb Space Telescope's infrared capabilities provide a different window into this chemical puzzle box. The carbon dioxide emissions that are opaque at the visible wavelengths become more transparent in the infrared, and allowing the JWST to probe deeper into the coma and potentially glimpse the features that are closer to the nucleus. However, even these advanced observations require a careful modeling to separate the genuine nucleus's properties from the effects of the surrounding atmosphere. The production rate calculations become particularly challenging in this environment because they depend on the assumptions about how a gas escapes from the nucleus and expands into a space. In a typical water-dominated coma, these calculations rely on the well-established models that were developed from the decades of the solar system comet observations. A Three Atlas's carbon dioxide dominance means that many of these standard assumptions might not apply, potentially leading to the systematic errors in our estimates of a gas production and a nucleus's properties. The chemical implications extend beyond the simple composition questions to the fundamental issues about a comet's formation environment. If a Three Atlas was formed in a stellar system with the different temperature profiles than our early solar nebula, it might have condensed from a gas mixture with the different ratios of a carbon dioxide to a water ice. Such formation conditions could exist around the stars that are cooler than our Sun, or in the regions of the protoplanetary disks where a carbon dioxide remains gaseous at the temperatures that would freeze a water. Alternatively, the carbon dioxide dominance might reflect a post-formation evolution during the object's journey through an interstellar space. A cosmic ray bombardment, an exposure to an interstellar radiation, and a chemical processing over the millions of the years could alter a surface's composition in the ways that affect the outgassing patterns when the object finally encounters another star. The puzzle box nature of these observations means that solving one mystery often reveals the additional questions that are underneath. An understanding the carbon dioxide production mechanisms might explain the uniform outgassing pattern, but it raises the new questions about a formation, an environment, and an evolutionary history. And explaining the chemical processing that creates such unusual composition ratios opens the inquiries about the stellar systems and the galactic environments that could produce such objects. As a Three Atlas continues its approach toward a perihelion, the carbon dioxide puzzle box will likely reveal the additional layers of a complexity. An increasing solar heating should drive the changes in the production rates, potentially revealing the jets or the active regions that are currently masked by a uniform outgassing. The different volatiles might begin sublimating as the surface's temperatures rise and adding the new chemical components to the already complex coma's composition. The ultimate resolution of this puzzle will likely require combining the observations across the multiple wavelengths, the instruments, and the observing epochs to build a complete picture of how a chemistry, a physics, and a history combine to create the unusual object that we observe today. Until then, the carbon dioxide shroud continues to guard its secrets with a chemical determination, reminding us that the cosmos still holds the mysteries that challenge our understanding of what is possible in a nature. If it is the natural explanation for a Three Atlas's unusual properties weaves together the threads of a stellar evolution, a planetary formation theory, and a cosmic chemistry into a narrative that stretches our understanding of how diverse the universe's comet population might be. If we are witnessing the purely natural phenomena, then this interstellar visitor represents a window into the formation environments and the evolutionary processes that differ dramatically from anything in our local cosmic neighborhood, potentially teaching us about the chemical diversity of the planetary systems across the galaxy. The formation environment hypothesis begins with the recognition that not all of the stars are created and equal. Our Sun was formed from a molecular cloud with a specific composition, a temperature profile, and a chemical evolution history that determined what kinds of the materials could condense at the different distances from the developing star. A comet that was forming around a different type of a star, perhaps a lower mass, a cooler red dwarf, or a star that was born in a galactic region with a different metallicity, might incorporate the ices and the dust with the compositions that seem exotic from our solar system's perspective. In such an environment, the ice line structure that determines where the different volatile compounds freeze out of the protoplanetary disk could be dramatically different from our early solar nebula. A water might remain gaseous at the distances where a carbon dioxide condenses into a solid form, creating a population of the comets that are naturally a carbon dioxide rich rather than a water dominated. This environmental explanation does not require any exotic physics, just the different initial conditions that reflect the diversity of the stellar formation environments across the galaxy. The surface evolution scenario provides another natural pathway to the chemistry that we observe. Over the millions of the years that a 3 Atlas spent journeying between the stellar systems, its surface would have been continuously bombarded by the cosmic rays and exposed to an interstellar radiation, and subject to a chemical processing that does not occur in the relatively protected environment of our solar system's Kuiper belt or the Oort cloud. Such a processing could create the insulating surface layers that selectively regulate an outgassing and allowing the more volatile compounds like a carbon dioxide to escape, while trapping the less volatile materials like a water ice beneath the surface. This mechanism could explain both the unusual carbon dioxide to a water ratio and the apparently uniform outgassing pattern. If a space weathering created a relatively homogeneous surface crust with the consistent thermal and the chemical properties, the result might be the featureless symmetric coma that makes a 3 Atlas so difficult to study. As the comet approaches a perihelion and the surface's temperatures rise, this insulating layer might begin to break down, potentially revealing the more conventional water-rich composition that lies beneath. The selective nickel release mechanism remains more speculative, but not beyond the realm of a known chemistry. In the carbon-rich environments, the transient metal carbonyls might form under the specific temperature and the pressure conditions, creating the volatile nickel compounds that can escape into the gas phase, while an iron remains bound in the less volatile forms. The laboratory studies of a metal carbonyl chemistry suggest that a nickel carbonyl can be more volatile than many of the iron carbonyls, potentially creating the selective metal release that we observe spectroscopically. Alternatively, the nickel-iron decoupling might reflect a compositional heterogeneity that was inherited from the comet's birth environment. If a 3 Atlas was formed from the materials that were naturally and enriched in a nickel relative to an iron, perhaps a condensing from a stellar wind or a supernova, ejecta with the unusual element ratios. The metal emissions that we observe might simply reflect this exotic but a natural composition. The size and the structural constraint from the Hubble's observations remain consistent with a natural small body. The upper limit of approximately 5.6 kilometers for a nucleus's diameter falls well within the range of the solar system's comets, and there is nothing about the dust production or a coma's morphology that requires anything that is beyond a conventional comet physics. The fact that the nucleus remains hidden behind its own emissions is an unusual but not an unprecedented. Some of the solar system's comets also develop the optically thick comas that obscure a direct observation of their solid cores. The temporal evolution of the chemical signatures provides a strong support for the natural processes. The emergence of the cyanide emissions in a mid-August coinciding with the nickel detections, and consistent with an increasing solar heating, follows the patterns that we would expect from a thermal evolution of the volatile rich materials. If a 3 Atlas were an artificial object, we might expect the more complex or the structured temporal behavior, rather than the steady increase in an activity that is driven by a straightforward heating as the object approaches the sun. The comparison with a Borisov offers both a reassurance and a caution for a natural interpretation. A Borisov proved to be entirely conventional in its chemistry, and a behavior demonstrating that the interstellar objects do not automatically imply the exotic origins. However, the fact that the two successive interstellar visitors have shown such different characteristics suggests that we are sampling a diverse population of the objects with a range of the formation histories and the evolutionary processes. If a 3 Atlas is indeed a natural, it provides an unprecedented insight into the diversity of the planetary formation environments across the galaxy. Every unusual characteristic, from the carbon dioxide dominance to the nickel-iron decoupling, becomes a clue about the stellar systems and the chemical processes that we cannot directly observe, but can infer from their frozen remnants that occasionally visit our cosmic neighborhood. The natural story also carries the implications for an astrobiology and a planetary science more broadly. If the comets can form with such dramatically different compositions depending on their stellar environment, then the delivery of the volatile compounds to the terrestrial planets might vary significantly across the different stellar systems. And understanding this compositional diversity becomes crucial for assessing the potential habitability of the exoplanets and the likelihood that the Earth-like worlds receive the chemical ingredients that are necessary for a life. The Mars-based observations that were planned for an early October could provide the crucial tests of a natural hypothesis. If a 3 Atlas shows the expected thermal evolution, it develops the asymmetric jets as its insulating crust breaks down, or it reveals the compositional changes that are consistent with a multi-layer structure. These observations would strongly support the natural formation and the evolution processes. The natural explanation for a 3 Atlas is satisfying in its scope and internally consistent in its logic. But like all of the good scientific hypotheses, it makes the testable predictions that can be confirmed or refuted by an additional observation. The ultimate test will be whether this natural story can account for all of the unusual properties that we observe, or whether the additional anomalies will emerge that push us toward the more exotic explanations. If it is not a natural, the possibility that a 3 Atlas might represent something that is beyond a natural comet, evolution requires a careful definition of what would constitute a credible evidence for a technological origin, as it is distinguished from the kind of a speculation that can flourish in a data gap. This thought experiment must be grounded in the same rigorous evidentiary standards that apply to any extraordinary scientific claim, while in acknowledging that our current observations fall far short of meeting those standards. The credible technosignatures would need to be both unambiguous in their artificial nature and reproducible across the independent observations. The engineered isotopic ratios that differ systematically from the solar system's norms might indicate the nucleosynthetic processes that do not occur in nature, but such measurements would require a precision that is beyond a current spectroscopic capability. The narrow-band radio emissions that were synchronized with the object's geometry or a rotational period could suggest an intentional transmission, but no such signals have been detected despite a radio telescope's monitoring effort. The structured radar echoes might reveal a geometric regularity that is inconsistent with the natural formation processes. If a 3 Atlas possessed the internal cavities, the regular surfaces, or the organized structural elements, these might be detectable through a radar observation when the object reaches the closer distances. However, a current radar capability is limited by the comet's distance and a relatively small size, which is making such observations technically challenging, even if the artificial structures were present. The non-gravitational accelerations provide another potential technosignature, but these must be distinguished carefully from the outgassing forces that naturally affect a comet's orbit. And Oumuamua showed an anomalous acceleration that initially sparked a speculation about an artificial propulsion before it was explained by an asymmetric outgassing of a hydrogen. Any acceleration anomaly in a 3 Atlas would need to show the patterns that are inconsistent with the known outgassing mechanisms, perhaps a too regular, a too directed, or an occurring at the times when the thermal conditions would not support a natural volatile release. The nickel without iron signature has been proposed in some of the commentary as a potentially indicative of an industrial processing, since a terrestrial metallurgy does produce the nickel-rich alloys with a minimal iron content. This represents an interesting speculation rather than an established fact, and it faces the challenge that an unusual chemistry does not automatically imply a technological origin. Many of the natural processes can create the element ratios that seem artificial from our limited terrestrial perspective. The absence of the obvious jets or the tails has also been cited as potentially suspicious, with the suggestions that the uniform outgassing pattern might indicate an artificial regulation of a gas release. However, this interpretation requires ignoring the observational limitations that were imposed by a viewing geometry, an instrumental resolution, and the carbon dioxide shroud that could easily mask the narrow jets or the asymmetric features. The natural comets do occasionally exhibit the surprisingly uniform outgassing, particularly when they are observed at a modest resolution or an unfavorable phase angle. What we definitively do not have are the multiple independent lines of evidence that are all pointing toward a technological origin. The unusual chemistry stands alone without the corroborating technosignatures that would be expected if we were truly observing an artificial object. There are no radio signals, no geometric structures that are visible in an imaging, no isotopic anomalies, and no acceleration patterns that are inconsistent with an outgassing. The absence of such supporting evidence does not prove a natural origin, but it does place the burden of a proof squarely on the claims of an artificial manufacture. A responsible evaluation of a technological possibility would require a multimodal evidence that was collected across the different types of the instruments and the analysis techniques. The spectroscopic anomalies would need to be confirmed by the isotopic measurements. The chemical signatures would need to be supported by the structural observations, and any single unusual characteristic could potentially be explained by the natural processes that we do not yet understand. But the multiple independent anomalies that are all pointing toward an artificial origin would be much more difficult to dismiss. The historical precedent of an Oumuamua provides both a caution and a context for evaluating the exotic hypotheses. The initial observations of that object's unusual acceleration and an elongated shape sparked a serious scientific discussion of a possible artificial origin, which was including the peer-reviewed papers that were exploring the technological explanations. However, a subsequent analysis and an additional observation eventually provided the natural explanations for most of the anomalous characteristics, demonstrating how easily the extraordinary claims can emerge from an incomplete data. The confirmation bias problem affects the technological speculations just as much as the conventional interpretations. When looking for an evidence of an artificial origin, it becomes tempting to interpret any unusual characteristic as supporting that hypothesis while downplaying the findings that suggest the natural processes. This psychological tendency requires a conscious effort to counteract demanding that the technological hypotheses be held to the same rigorous evidentiary standards as any other scientific claim. The time-resolved observations across a perihelion passage could provide the crucial tests of a technological hypothesis. If a Three Atlas were an artificial object that was designed to appear a comet-like, we might expect its behavior to diverge from a natural thermal evolution as a solar heating increases. Conversely, if its chemical and a physical evolution follows the predictable patterns that are driven by an increasing temperature and a changing illumination condition, this would strengthen the case for a natural origin. An isotopic measurement represents perhaps the most definitive test of a natural versus an artificial origin. Every stellar system has a unique isotopic fingerprint that is reflecting its formation history and its nucleosynthetic process. The natural objects carry the isotopic ratios that reflect their birth environment, while the artificial objects might show the isotopic signatures that reflect a technological processing or the material sources that do not occur in nature. Such measurements push a current spectroscopic capability to its limit, but could provide an unambiguous evidence for an exotic origin if the anomalous ratios were detected. The coordinated radio search efforts that have monitored a Three Atlas represent exactly the kind of a systematic investigation that a technological hypothesis requires. The absence of the detected signals does not definitively rule out an artificial origin. Any hypothetical technology might not emit in a radio frequency or might be designed to appear unnatural, but it does eliminate one of the most obvious potential technosignatures. If we engage in the thought experiment of what a discovery of a genuine artificial origin would mean, the implications extend far beyond an astronomy to the fundamental questions about an intelligence, a technology, and our place in the cosmic community. Such a discovery would represent a confirmation that the technological civilizations exist elsewhere in the universe and possess the capabilities for an interstellar travel or a communication. The scientific and the philosophical implications would be profound enough to justify the extraordinary evidentiary standards that any such claim must meet. For now, the technological hypothesis remains an intriguing possibility that serves an important function in ensuring that we consider all of the reasonable explanations for the unusual observations. But a speculation must be clearly distinguished from an evidence, and an extraordinary claim must await an extraordinary proof. The mission temptation. The prospect of intercepting a Three Atlas with a spacecraft represents one of those tantalizing missed opportunities that will haunt the mission planners for the decades, a chance to study an interstellar visitor up close that arrived with just enough in advance notice to make us to realize what we could have done, but not enough a lead time to actually do it. The physics of an orbital mechanics and a spacecraft design create a cruel irony. The more an unusual and a scientifically interesting an object appears, the more desperately that we want to send a probe to investigate, and the more impossible that such a mission becomes with an existing technology and a planning timeline. The reality of launching a bespoke interception mission to a 3 Atlas confronts the fundamental limitations of a current spaceflight capability. Designing a building and launching a spacecraft requires the years of a preparation under the ideal circumstances. The fastest planetary missions in NASA's history, which were including the New Horizons probe to Pluto, required nearly a decade from an initial concept to a launch. A 3 Atlas was discovered in July 2025 with a perihelion date in late October, barely 4 months of a warning for what would need to be the most rapidly executed deep space mission that was ever attempted. Even if the technical challenges could be overcome, the velocity requirements for intercepting a hyperbolic trajectory object are staggering. Unlike the solar system's planets that follow the predictable elliptical orbits, the interstellar visitors arrive with an excess velocity that our chemical rockets can barely match. Reaching a 3 Atlas would require a spacecraft to achieve a delta V, a change in a velocity that was comparable to or exceeding the most ambitious missions that were ever flown, and to do so within a launch window that was measured in the weeks rather than the years that were typically available for the planetary missions. However, the astronomical community has not been sitting idle while a 3 Atlas approaches its closest solar passage. An opportunistic observation that is using the existing assets represents the practical response to this mission temptation. The European Space Agency's Mars orbiters, which were originally designed to study the red planet's atmosphere and its surface, are being redirected to observe a 3 Atlas during the comet's closest approach to Mars on approximately October 3, 2025, when the two objects will be separated by only about 30 million kilometers. This Mars-based observation campaign represents a compromise between the impossible dream of a dedicated interception mission and the limitations of a purely Earth-based telescopy. From Mars's vantage point, a 3 Atlas will appear to be significantly brighter and larger than from the Earth, potentially allowing the detailed observations of a comet's structure, a nucleus's property, and a temporal evolution that would be difficult or impossible to achieve from our home planet. The red planet essentially becomes a temporary deep space observatory, providing a closer perspective on the interstellar visitor without requiring a purpose-built spacecraft. The coordination between the Hubble, the James Webb, and the Sphere-X demonstrates how the astronomical community maximizes a scientific return when a physical interception is not possible. These complementary observations across the different wavelength ranges provide a comprehensive view of a 3 Atlas's properties that no single instrument could achieve alone. The Hubble contributes a high-resolution imaging in visible light, the JWST provides a detailed spectroscopy in the infrared, and the Sphere-X adds a wide-field context and an additional spectroscopic capability. A public proposal to retarget the existing deep space missions has surfaced in the various forums, which are including the suggestions to redirect the spacecraft like the Juno or other outer solar systems probes toward a 3 Atlas. While such ideas demonstrate a creative thinking about utilizing the existing assets, they face the practical challenges, which are including a fuel limitation, a communication constraint, and the fundamental physics of changing a spacecraft's trajectory from one target to another. Most of the deep space probes are designed with the specific mission profiles that leave little room for the major course corrections. The broader lesson that is emerging from this mission temptation involves the need for the standing capabilities to respond to the unexpected discoveries. Project Lyra and the similar conceptual studies have explored what a rapid response interstellar object mission would require: a pre-positioned spacecraft, an advanced propulsion system, and a decision-making process that can operate on the timelines that were measured in the months rather than the years. Such capabilities do not currently exist, but represent the logical extensions of a current space technology development. The Southwest Research Institute and other organizations have conducted the preliminary studies of the intercept mission architectures and examining the trade-offs between a launch capability, a propulsion technology, and a scientific payload that would enable the meaningful encounters with the interstellar objects. These analyses suggest that while they are challenging, such missions are within the realm of a possibility, given a sufficient advanced preparation and a dedicated resource. The institutional dynamics that are around a potential intercept mission reveal the conservative nature of a space agency's decision-making process. The NASA and the ESA operate under the budget cycles and the planning horizons that are fundamentally incompatible with the rapid response times that are required for the interstellar object encounters. Even if the technical solutions existed, the bureaucratic and the financial mechanisms for implementing such missions on a short notice remain underdeveloped. A future preparedness requires not just a technological development but an institutional innovation, a decision-making process that can evaluate and approve the missions on the timelines that were measured in the months, a pre-approved budget that can be rapidly deployed for the unexpected opportunities, and an international coordination mechanism that can combine the resources from the multiple space agencies when the extraordinary opportunities arise. The specific case of a 3 Atlas illustrates both the promise and the limitations of this approach. If the Mars-based observations reveal the additional anomalies or confirm the unusual characteristics that were already detected from the Earth, the scientific community will have demonstrated that a creative use of the existing assets can yield the significant results. However, many of the fundamental questions about the object's composition, its structure, and its origin will remain unanswerable only through a direct spacecraft investigation. The timeline pressure that was created by the interstellar object encounters also highlights the importance of the ground-based and the space-based survey systems that can provide an earlier warning of the incoming visitors. The earlier that an interstellar object is detected, the more time that the mission planners have to evaluate the intercept possibilities and to develop the appropriate responses. The projects like the Vera C. Rubin Observatory and the proposed NEO Surveyor mission could dramatically improve our ability to spot such objects with a sufficient advance notice to enable the meaningful spacecraft missions. Perhaps most importantly, the mission temptation that was generated by a 3 Atlas serves as a reminder that the universe operates on its own schedule, not ours. An extraordinary opportunity for a scientific discovery arrives when it arrives, not when we are prepared for it. The question that is facing the space community is whether we will be better positioned to respond when the next interstellar visitor makes its appearance, or whether we will once again find ourselves watching from afar as the cosmic mysteries pass through our solar system and disappear forever into the galactic night. The calendar. A time moves differently for the interstellar visitors than it does for those of us who are bound to the Earth's daily rhythms. While we measure our lives in the seasons and the years, a 3 Atlas follows a cosmic calendar that is written in a gravitational mathematics, its schedule that is determined by the precise choreography of an orbital mechanics rather than a human convenience or a curiosity. An understanding this temporal framework becomes essential for appreciating both what we have already learned and what opportunities remain for unraveling its mysteries. The discovery date of July 1, 2025 marks more than just the moment when the automated telescopes at the Atlas facility in Chile first noticed an unusual point of a light that was moving against the starfield. It represents the beginning of a precisely defined observational window that will close forever when this interstellar visitor exits our solar system and returns to the galactic void. Unlike the planets, the asteroids, and the comets that are native to our solar system, a 3 Atlas offers no second chances, no future orbital returns that might provide the additional opportunities for a study. The approach to a perihelion, the closest solar distance that is scheduled for approximately October 30, 2025, at a roughly 1.4 astronomical units from the Sun, represents the climactic moment of this cosmic performance. At this distance, which is just inside of Mars's orbital radius, a 3 Atlas will experience a maximum solar heating and presumably a maximum activity. If the comet is going to reveal the additional secrets about its composition, its structure, or its behavior, this period that is around a perihelion offers the best opportunity for such revelations. The Mars geometry adds a crucial subplot to this temporal narrative. On approximately October 3, 2025, a 3 Atlas will pass within roughly 30 million kilometers of a cosmic close encounter that positions the red planet as an opportunistic observation platform. This proximity offers the European Space Agency's orbiters that are currently studying Mars a unique chance to observe the interstellar visitor from a vantage point that is much closer than the Earth's, potentially providing a detail and a perspective that are impossible to achieve from our home planet. The observational calendar, however, is complicated by the inexorable mechanics of an orbital geometry. As a 3 Atlas approaches a perihelion and then begins its journey back to an interstellar space, its apparent position as it is seen from the Earth will bring it progressively closer to the Sun in our sky. Sometime in late September or early October, the comet will become too close to the Sun's glare for a safe observation by most of the Earth-based telescopes and entering what the astronomers call the zone of a solar conjunction. This observational blackout period that is lasting through most of a November represents one of the most frustrating aspects of studying a 3 Atlas. Just when the comet should be at its most active and potentially most revealing, it disappears behind the sun's overwhelming brightness from the Earth's perspective. The space-based telescopes like the Hubble and the James Webb have some capability to observe closer to the sun than the ground-based facilities, but even they face the limitations when the targets approach too near to our star's position. The emergence from a solar conjunction in an early December 2025 offers what may be our final extended opportunity to study a 3 Atlas before it fades beyond the reach of current instrumentation. By this time, the comet will be receding from the sun and likely decreasing in activity, but it will once again be positioned for an observation by the full suite of the Earth-based and the space-based facilities that have been tracking its approach. This post-perihelion observation period will be crucial for an understanding how a 3 Atlas responds to a decreasing solar heating. If the unusual chemical signatures that were observed during its approach, the nickel without an iron, the carbon dioxide dominance, and the cyanide emergence, show a predictable evolution as the comet cools, this would support the natural formation and the evolution hypotheses. Conversely, any unexpected change or an anomalous behavior during the cooling phase could provide the additional clues about the object's true nature. The preprint and the peer review timeline adds another temporal dimension to this unfolding story. The scientific papers that are documenting the observations from July through September 2025 have already begun and appearing on the RxIve, with the initial findings that are available the weeks or the months before a formal peer review. However, the definitive analyses that are incorporating the complete observational dataset from a discovery through a final visibility will not be available until well into 2026, long after a 3 Atlas has disappeared from a telescopic view. This lag between an observation and a complete analysis creates a peculiar information environment where the most interesting preliminary findings are available quickly, but must be interpreted with an appropriate caution that is pending a more thorough evaluation. The nickel detections, the carbon dioxide ratios, and other anomalous characteristics currently represent a work in progress, rather than a settled science, even as they drive a public interest and a scientific speculation. The James Webb Space Telescope, the Hubble Space Telescope, and the Spherix observing schedules operate according to their own complex cadences of the target priorities, the orbital constraints, and the data processing timelines. The observations that were made in August might not be fully analyzed and released until in October or in November, creating the situations where the most detailed findings about a 3 Atlas's properties might not become available until after the object has disappeared into a solar conjunction. A public communication timeline adds yet another layer to this temporal complexity. The NASA and the ESA typically maintain the conservative schedules for releasing the observational results, preferring to allow the peer review processes to run their course before making the strong claims about the potentially significant discoveries. This institutional caution, while it is scientifically responsible, can create the information gaps that a speculative coverage rushes to fill during the months that are between the initial observations and a formal publication. The safety reminder that threads through every official timeline discussion that a 3 Atlas poses no threat to the Earth at any point in its trajectory reflects an institutional recognition that the cosmic mysteries can spark a public concern. By maintaining a clear communication about the orbital parameters and the closest approach distances, the space agencies provide a reassurance while allowing a scientific investigation to proceed without an unnecessary alarm. Perhaps most poignantly, the calendar of a 3 Atlas represents a cosmic reminder that the universe operates on its own schedule, which is indifferent to a human convenience or a preparation. This interstellar visitor arrived when it arrived. It will reach a perihelion when an orbital mechanics dictates, and it will depart according to the mathematics of a hyperbolic trajectory. Our role as the observers is to make the most of the opportunities that were provided, and understanding that some of the questions may remain forever and unanswered simply because the cosmos does not arrange its schedule around our curiosity. The turning of the calendar pages toward a late October and an early December 2025 marks more than just the passage of a time. It represents the closing of a cosmic window that will never open again. When a 3 Atlas finally fades beyond the reach of our most sensitive instruments, It will carry with it whatever secrets that we have not managed to unlock, leaving behind only the data that we have collected and the questions that we have learned to ask. Reading between the lines, the phrase, "what the scientists aren't telling us," typically implies a deliberate concealment or a conspiracy, but in the case of a Three Atlas, it more accurately describes the careful boundaries between what can be responsibly concluded from a current data and what must remain in the realm of a speculation until an additional evidence becomes available. The gap between a public curiosity and a scientific certainty is not an evidence of a secrecy. It is a reflection of how a knowledge gets constructed from an incomplete information under the conditions of a genuine uncertainty. The pending question of a nickel without iron's robustness illustrates this distinction perfectly. The multiple independent teams that are using the different instruments have reported the neutral nickel emission lines without the accompanying iron signatures in their spectra of a Three Atlas. This represents a genuine observational result that has been reproduced across the several facilities and the analysis methods. However, the mechanism that produces this unusual chemistry remains unknown, and the reproducibility across the different observing epochs and the geometric conditions has not yet been fully established. What would constitute a definitive confirmation of this anomaly? The same spectroscopic signatures would need to appear consistently as a Three Atlas approaches a perihelion and a solar heating increases. The different instruments that are observing at the different wavelengths would need to show the compatible results, and the temporal evolution of the nickel emissions would need to follow the patterns that are consistent with the thermal models of a nucleus's heating. Only when these multiple lines of an evidence converge can the scientific community move from an interesting, if true, to an established phenomenon that is requiring an explanation. The question of a nucleus's size and a shape under the carbon dioxide shroud represents another pending mystery that illustrates the limitations of a current observation. The Hubble's upper limit of an approximately 5.6 kilometers provides a constraint rather than a measurement, and establishing what the nucleus cannot be rather than what it is. The actual solid core could be significantly smaller and irregularly shaped or possess the surface features that remain invisible behind the optically thick coma. A future observation might resolve this uncertainty through the several approaches. A radar observation, if the comet passes within a range of the planetary radar systems, could potentially penetrate the coma and map the nuclear surface directly. A thermal infrared observation might detect a heat emission from the solid core that is less affected by a gas absorption than a visible light. Most intriguingly, if the carbon dioxide shroud begins to dissipate as the comet recedes from the sun post-perihelion, a direct optical observation of the nucleus might finally become possible. The jets and the tails question highlights how the observational limitations can create the apparent mysteries that later resolve with a better data or the different viewing conditions. The current reports of no obvious jets or a featureless coma must be understood as an epoch-specific and an instrument-limited, rather than the definitive characteristics of the object. The jets that are narrow, pointing in the unfavorable directions, or obscured by the carbon dioxide shroud, might become visible under the different geometric conditions or with the higher resolution observations. The Mars-based observations that were planned for an early October represent perhaps the best opportunity to resolve this uncertainty. The European Space Agency's orbiters that are positioned much closer to a Three Atlas than the Earth-based telescopes might detect the jets, the streamers, or the asymmetric features that are below the detection threshold from our home planet. If such features appear in a Mars Vantage observation, it would demonstrate that the apparent uniformity that was seen from the Earth reflects the observational limitations rather than a genuine absence of a structure. The carbon dioxide to a water ratio represents another measurement that exists in the uncertain territory between a preliminary finding and an established fact. The multiple outlets have reported the ratios that are around an 8:1 carbon dioxide to a water, but these numbers come from an analysis of the single epoch observations that may not represent the comet's full compositional story. As a solar heating increases toward a perihelion, the relative production of the different volatiles could change dramatically, potentially revealing a more conventional water-rich composition that is beneath the surface layer that currently dominates an outgassing. A peer-reviewed confirmation of these ratios will require a careful cross-calibration between the different instruments and the observing epochs, along with a thermal modeling that can account for how a changing solar distance affects the relative sublimation of the different ice types. The precise numbers may shift as the analysis techniques are refined and an additional data become available. But the general pattern of a carbon dioxide dominance appears to be consistent across the multiple observational approaches. The cyanide emergence that was documented in a mid-August observation provides another piece of this evolving chemical puzzle. The temporal correlation between a cyanide detection and a nickel emission suggests that we are watching a complex chemical system that is responding to an increasing solar heating. However, the parent molecules that produce the cyanide radicals, the specific thermal conditions that are required for their release, and the implications for an overall nucleus's composition remain the subjects of an ongoing analysis. The coordination between the James Webb Space Telescope, the Hubble Space Telescope, the SphereX, and the ground-based facilities represents an unprecedented multi-wavelength campaign to study an interstellar object. Each instrument contributes the unique capabilities: the Hubble's high-resolution imaging, the JWST's detailed infrared spectroscopy, and the SphereX's wide-field coverage. But synthesizing these observations into a coherent picture of a Three Atlas requires a careful attention to the systematic differences between the facilities and the observation epochs. This synthesis process takes a time which is often in extending the months beyond the initial observations, as the teams work to understand how an instrumental systematic, a calibration uncertainty, and a temporal evolution affect their measurements. The most complete scientific picture of a Three Atlas will likely emerge only in a late 2025 or an early 2026, well after the object has disappeared from a view, but when a sufficient time has passed for a thorough analysis and a cross-validation. A media literacy becomes particularly important during this period of an evolving understanding. The news summaries of the preprint papers provide a valuable accessibility to the technical findings, but may and inadvertently present the preliminary results with a greater certainty than the original authors intended. The commentary and the opinion pieces, regardless of their quality, represent the interpretive frameworks rather than the established facts, and should be distinguished clearly from the observational data and the peer-reviewed analysis. The distinction between a "we don't know" and a "we can't say" reveals the different types of an uncertainty that affects a scientific communication about a Three Atlas. A "we don't know" implies that a current data is insufficient to determine the answer, but an additional observation might resolve the question. A "we can't say" suggests that the data might be inadequate, but that a responsible scientific practice requires a waiting for a peer review, a replication, or a theoretical development before drawing the conclusions. Both of the types of an uncertainty reflect the careful process by which a reliable knowledge gets constructed from a partial information. In an astronomy where the phenomena often occur on the timescales and the distance scales that preclude a controlled experimentation, this conservative approach becomes particularly important for maintaining a public trust in the scientific institutions and in avoiding the kind of a spectacular retraction that can undermine a confidence in the research process. The questions that will likely persist even after a Three Atlas disappears from a view illustrate the inherent limitations of studying the interstellar visitors with a current technology. We may never know the exact composition of the nucleus's core, the details of its formation environment, or the complete story of its journey through space. Some of the mysteries may remain forever and unsolved simply because the observational opportunities were too brief and the technical challenges were too great for a complete resolution. This acceptance of a partial knowledge represents a mature understanding of how a science operates at the frontiers of the possible. Not every question has a definitive answer. Not every mystery yields to an investigation, and not every unusual phenomenon can be fully explained with a current tool and a technique. The value lies not in a complete resolution, but in the advancement of an understanding, the refinement of the questions, and the preparation for the better investigations when the similar opportunities arise in the future. A reading between the lines of a scientific communication about a Three Atlas reveals not a conspiracy or a cover-up, but the careful work of constructing a reliable knowledge under the conditions of a genuine uncertainty. The gaps in our understanding represent not the failures of an investigation, but the natural boundaries between what a current evidence supports and what remains to be discovered. Drift into a sleep. As we near the end of our journey through the mysteries that are surrounding a Three Atlas, the cosmic visitor that arrived from an interstellar space that was wrapped in the chemical enigmas and the spectroscopic whispers, It is worth a pausing to reflect on what this story tells us about our place in a universe that is far stranger and more diverse than we sometimes dare to imagine. Here is an object that traveled perhaps the millions of the years through the galactic void, carrying within its frozen nucleus the chemical fingerprints of the stellar systems that we may never see, only to grace our solar system with a brief visit that challenges our understanding of what is possible in a nature. The nickel without an iron remains a gentle mystery which is reproducible across the multiple instruments, yet unexplained by a current theory. Like a cosmic riddle that was written in the wavelengths of a light, it reminds us that the universe still holds the secrets that do not yield easily to our most sophisticated analysis. Whether this unusual chemistry reflects the exotic formation environments that are around the distant stars, a processing by an interstellar radiation during the eons of a cosmic wandering, or the mechanisms that we have not yet learned to recognize, it speaks to the diversity of the conditions and the processes that exist beyond our familiar solar neighborhood. The carbon dioxide shroud that conceals a Three Atlas's nucleus serves as a metaphor for the partial knowledge that characterizes so much of an astronomy. We see what the comet chooses to reveal: its gaseous emissions, its dusty coma, and the spectral signatures of the molecules that are escaping into a space, while the solid core that contains the answers to our most fundamental questions remains hidden behind its own atmospheric veil. This concealment is not a deliberate obscurity, but simply the way that the complex natural systems interact with the tools that we have available to study them. The temporal evolution that we have witnessed from the quiet July discovery through the emergence of the cyanide emissions in an August to the approaching perihelion drama of a late October illustrates how the astronomical objects exist in their own time, following the schedules that were written in an orbital mechanics rather than a human curiosity. We are the observers of a performance that began the millions of the years ago and will conclude when a Three Atlas disappears into the cosmic dark, leaving behind only the data that we have managed to collect during this brief intersection of the trajectories. The careful language of a scientific communication, the analysis ongoing, the preliminary results, and the further observations planned reflects not an institutional secrecy, but an intellectual humility in the face of a genuine uncertainty. When it is confronted with the phenomena that do not fit the established models, a responsible science proceeds with the kind of a methodical caution that can seem frustrating to those who are seeking the immediate answers, but that ultimately produces a knowledge that is reliable enough to build upon. This is perhaps the most profound lesson that is embedded in the Three Atlas's story, that a silence often indicates a care rather than a concealment, that the unanswered questions represent the opportunities for a discovery rather than the failures of an investigation, and that the boundaries of our knowledge define not the limitations, but the frontiers that are waiting to be explored. Consider the two narrative paths that remain open as we drift towards a sleep. In one of the stories, a Three Atlas represents the natural but the exotic product of the stellar environments that are unlike our own, a cosmic ambassador that is carrying the chemical signature of the formation processes that operate under the conditions that are different from those that created our familiar solar system. Its unusual properties become the windows into the diversity of a planetary formation across the galaxy, teaching us that the universe creates the comets in the ways that we have not yet learned to expect. In the alternative story, which is presented clearly as a speculation rather than a conclusion, a Three Atlas might represent something that challenges our assumptions about what occurs naturally in the cosmos. The combination of an unusual chemistry, a hidden structure, and an anomalous behavior might point toward the processes or the origins that stretch the boundaries of a conventional explanation, and opening the questions that could reshape our understanding of what is possible in the universe that we inhabit. Both of the stories remain consistent with a current observation, and both of them will likely persist until an additional data tips the balance of an evidence toward one interpretation or another. This coexistence of the possibilities is not a failure of a scientific method, but an honest acknowledgement that the complex phenomena often admit the multiple explanations until a sufficient evidence accumulates to distinguish between them. The observations that were planned for the coming weeks, the Mars Vantage studies, the perihelion monitoring, and the post-conjunction follow-up will add the new chapters to this unfolding story. Each spectrum, each image, and each measurement will either support or challenge the existing hypotheses, gradually building the evidentiary foundation that is needed for the confident conclusions. But even after a Three Atlas fades beyond the reach of our instruments, some of the questions will likely remain open, awaiting the next interstellar visitor to provide the additional pieces of the cosmic puzzle. This is the nature of a frontier science, the partial answers that are leading to the better questions, the mysteries that reveal the deeper mysteries, and a knowledge that grows through the patient accumulation of the observations and the careful evaluation of an evidence. The universe operates on the scales of a time and a distance that dwarf a human experience, following the physical laws that sometimes produce the phenomena that seem impossible until we learn to understand them. As we let these questions to rest for now, which were carried by the gentle current of a cosmic time toward whatever revelations that are awaiting, we can find a peace in the knowledge that the same sky under which we sleep is crossed by the visitors from the distant stars, carrying the stories that were written in a chemistry and a physics that we are slowly learning to read. The cosmos whispers its secrets in the many languages in the nickel emissions, and the carbon dioxide shrouds in an orbital mechanics and the spectroscopic signatures. And we are gradually becoming fluent in its vocabulary, asleep well under the same sky that a Three Atlas is crossing on its journey from one stellar system to another, carrying its mysteries through the space that is between the worlds. When you wake, it will be a little closer to a perihelion, a little more active and a little more willing perhaps to reveal the secrets that it has guarded during its long journey through the galactic night. The calendar pages turn toward a late October 2025 when this interstellar wanderer will make its closest approach to our sun before beginning its journey back to the cosmic void. An update will come as the data matures, as the peer review processes run their course, and as the careful work of a science transforms the observations into an understanding. But for now, in the quiet hours when the universe reveals its most profound truths, we can simply rest in the wonder of a knowing that we share the cosmos with the visitors from the other worlds, and that some of the mysteries are worth contemplating in the gentle darkness that bridges our small lives to the infinite expanse that is beyond.